In this video, we will briefly discuss the consequences, the three main consequences of the special theory of relativity, namely the length contraction, time dilation, and relative mass. We will majorly be focusing on the Python side of in this video, how to program them, how to maybe make them a little bit efficient, and we'll see what we can do as we move on. However, I will also discuss relativity a little bit, time dilation, length contraction, and relative mass as well. So let's start with the special relativity. Here it is. So here it says, in physics, the special theory of relativity, or special relativity for short, is a scientific theory regarding the relationship between space and time. Here, this space and time. Okay, so why is it called the special relativity? Actually, it is a special case from the general relativity, which was derived later and published in 1915 by Albert Einstein as well. The special theory of relativity deals with the space and time in the absence of strong gravitational fields. Okay, again it says, in Albert Einstein's original treatment, the theory is based on two postulates. The laws of physics are invariant, that is, identical in all inertial frame of reference, and the speed of light in vacuum is the same for all observers regardless of the motion of the light source or the observer. So what is the meaning of these two postulates? First of all, the first one is quite straightforward. The laws of physics are invariant or are identical in all inertial frame of reference. So the inertial frame of reference is such a reference in which you cannot detect acceleration of the object if you are in the same frame of reference as the object is. So if a bullet is traveling which has been fired from a gun, if you were to measure the acceleration of the bullet in the frame of reference of bullet, you will measure zero acceleration. However, there are different inertial frame of reference. For example, if you are observing from wherever you are observing the bullet will have acceleration in your frame of reference. And then the second postulate is that the speed of light in vacuum is same for all the observer. Whoever will observe the speed of light, it will measure always the same value, 299792458 meters per second. It doesn't matter if the source is moving, it doesn't matter if the source is receding, it doesn't matter if the observer is moving or receding. If the measurement is done in the vacuum, the speed of light will always be the constant 299792458 meters per second. That being said, we will discuss, as I said, only three major consequences of special theory of relativity: the length contraction, time dilation, and the relative mass. So let's go to the time dilation first. Time dilation. So it says, in physics and relativity, time dilation is the difference in the elapsed time as measured by two clocks. Let's say you're an observer standing in space. Somehow you are still alive and then you see a spaceship flying past you with relative speeds. Relative speeds are the speeds that are comparable to the speed of light. So what it means, what time dilation says, is that the time elapsed or the time passed in the spaceship's frame of reference will be different than what has been elapsed in your frame of reference. And if we come to the formulation of it, this delta t prime equals to delta t over square root of 1 over 1 minus v square over c square. V square is the velocity of the object or the spacecraft. C square is obviously the square of the speed of light. Delta t is the time passed in the frame of reference of the object itself, or spacecraft in our case, and delta t prime is the time elapsed that we will be measuring. So what it says is that the delta t prime will be different from the delta t that is elapsed in spacecraft. Coming to the other one, the length contraction, It says length contraction is the phenomena that a moving object's length is measured to be shorter than its proper length, which is the length as measured in the object's own rest frame of reference. Let's say we are again standing in space and a spacecraft flies past us at relativistic speeds. Let's say the spacecraft is of 1 meter length and it is moving near the speed of light. So what will happen is that the spacecraft itself actually will obviously be of 1 meter in length. However, for us, the observer that are observing the spacecraft, the length of the spacecraft will contract as the spacecraft moves closer and closer to the speed of light. Let's move on to the non-proper length. Okay, this is the formula. This is the short version. Here, this is a formula again. L equals L naught square root of 1 minus v square over c square. L naught is the proper length of the spaceship that is measured in the frame of reference of the spaceship itself. L is the length of the spaceship as we will measure in our frame of reference. Let's move on to the last one, relativistic mass. Okay, so relativistic mass. There is a distinction in relativistic and inertial mass. First, we need to define both of these masses and then we can move on. Let's say the spacecraft that we have been observing in space is at rest and it weighs 500 kilograms. That rest mass of 500 kilogram is the inertial mass of the spacecraft. Now the relativistic mass is when the spacecraft is moving, the sum of its energy and the rest mass is called the relativistic mass. So you can say let's just suppose that when the spacecraft is moving, it only has kinetic energy in it. So at that time, the relativistic mass will be the rest mass of the spacecraft and the kinetic energy that it possesses due to moving at the speed, at whatever speed it is moving with. So that is relativistic mass. And both these masses also differ, as you can see in this formula. Mass of relativistic mass is equal to the inertial mass divided by square root of 1 minus v square over c square. It is much like the time dilation formula, in which sense that the relativistic mass is always greater than the inertial mass, and the observed time from an external observer's perspective is always greater than the time elapsed in the inertial frame of reference for the object itself. A great example of this with respect to the time dilation is the Muon decay time. Let me see where it is. Yeah. Okay, so there there is this example. So let's see this example. Suppose a cosmic ray colliding with the nucleus in Earth's upper atmosphere produces a muon that has a velocity of v equals 0.95 c, or it is traveling at 95% the speed of light. The muon then travels at a constant velocity and lives 2.2 microseconds as measured in the muon's frame of reference. Okay, so what it says is that the muon that is produced, muon or muon, whatever you want to call it, that produced lives only for 2.2 microseconds in its own frame of reference. However, when we include the relativistic speeds here, v equals to 0.95 c, we can apply the formula for time dilation, and the time span that the muon can exist for an external observer that is observing it is 7.05 microseconds. That is roughly 3 times greater than its rest frame time for existence. However, a distinction should be made here that the muon will only live for 2.2 microsecond, or technically speaking will decay after 2.2 microsecond. However, for us, the observers that are watching it move with the relativistic velocity of 0.95 c, it will seem that the muon has decayed after 7.05 microsecond. Similarly, for the length contraction, the length of the object obviously does not change. It changes in our frame of reference when we are watching the object move with the relativistic speeds. Okay, so that's that. Now let's activate our spider and try to work them all in Python.